Hi, my name is Sukhmani Sethi, and this is my lab report for Physics Lab 4. The purpose of this lab is to examine the motion of a spring mass system where the mass oscillates and swings in an arc, and to compare the observed motion to a computational model of the predicted motion. The system consists of the spring mass in the Earth, and the surroundings consist of the universe. The result is that the system's total energy remains constantly at zero, which shows that the model demonstrates the energy principle. Fundamental principles used in this lab include the energy principle and Newton's second law. Newton's second law states that the motion of the oscillating mass is determined by the changes in its momentum, which are proportional to the net forces acting on it, such as the force from the spring and the force of gravity. The energy principle explains that the total energy of the system changes due to the work done by the external forces, such as the spring force and gravity. This energy exchange can be observed and tracked through the motion of the system. Newton's second law allows us to derive the velocity update formula and relate momentum to force and time. Using this, we can predict how the mass's speed and direction will change as it moves. Hooke's law explains that the spring force depends on how far the mass is stretched or compressed from its resting position. The farther the spring is stretched, the stronger the restoring force that tries to bring the mass back to its equilibrium position. The energy principle states that the total energy of the system, which includes the kinetic energy, the spring's potential energy, and the gravitational potential energy, remains constant. These equations help track how energy shifts between these different forms as the mass oscillates, ensuring that the energy is conserved throughout the motion. The video provided was uploaded to the tracker software, and the object was tracked per frame to find the x and y positions of the oscillatory motion and produced the following graphs. The x and y positions were then copied into a Google Sheets and downloaded as a CSV file and uploaded to the gross script model. The string constant, mass, and relaxed length of the string were updated by using the calculations shown in the preview video. The initial position and velocity of the object were modified to match the observations from the video, providing starting values for the equations of motion. The spring constant and relaxed length were updated using Hooke's law, which determines the restoring force based on the spring's stiffness and stretch. The code was modified to calculate the spring's length, direction, and stretch using the object's position in Hooke's law. The code was modified to calculate the system's total energy using the equations for kinetic energy, spring potential energy, and gravitational potential energy. Gravitational and spring forces were computed by using the equation for gravitational force and Hooke's law. Newton's second law and the kinematic equation for velocity were applied to update the object's velocity and position over time. After each movement, the spring's length and orientation were recalculated using Hooke's law to determine its new stretch and direction. Finally, the changes in kinetic, spring potential, and gravitational potential energies were recalculated and compared to the initial values. The resulting graphs show that the computational model was a lot smoother, whereas the actual data was more rough, which is most likely due to the air resistance that wasn't considered by the model. The energy principle was satisfied as the orange line is constant at zero, meaning that the total energy was always zero and the energy was conserved. The computational model accurately follows the energy principle, showing that the changes in kinetic, spring potential, and gravitational potential energy always balanced out and kept the system's total energy unchanged. Using the data obtained in Tracker, the estimated oscillation period of X was found to be 1.601 seconds, and the oscillation period for Y was found to be 1.698 seconds. This was found by subtracting the start and end times of a period found on one of the graphs. And the difference between these are due to the spring's vertical direction. The Y estimation is probably going to be more accurate than the X because the vertical oscillation was more precise. And the errors of this lab include air resistance, as the code did not account for it in its calculations. Thank you.